Welcome to the world of
Semiconductors.
In a moment, you will meet someone who will take you on a mysterious journey in which you will get to know
About semiconductors.
I'm sure many of you have heard about semiconductors, as we use them in our daily lives. In regards to electrical conductivity, there are three types. The first is insulators. These don't conduct electricity. Examples include rubber, glass, or a piece of wood. On the other hand, we have conductors, which are really good at conducting electricity. So these are a piece of aluminum or other metals, such as silver or gold. In between, we have semiconductors. These have mediocre conducting properties and are elements known as metalloids. Examples include germanium and silicon. The development of semiconductor-based technology is deep-rooted within quantum dynamics. A very important part is the Schrödinger equation, which has been essential in the development of the field. The Schrödinger equation provides a way to calculate the wave function psi and predict how it changes over time. Although it is very complex, even for a 1D scenario, we'll show some practical applications and uses. The wave function squared is equivalent to the probability density function, which describes the probability of where an electron will be. This is some of the probability density functions for different nodes, nodal numbers in a 1D box. As you can see here, the probability that the electron is at this point is the highest, and it is not likely to be on the ends. For these ones, there are nodes where there is zero probability that the electron will be, and these are used to predict the shapes of orbitals like s orbitals, p orbitals, d orbitals. These orbitals are created from wave functions. The Schrödinger equation led to the development of the theory linear combination of atomic orbitals into molecular orbitals, or LCAO-MO. It describes how two atomic orbitals can combine to form two molecular orbitals. In this example, two 1s hydrogen atomic orbitals combine to form a bonding orbital, which is lower in energy, and an anti-bonding molecular orbital, which is higher in energy. As you can see here, as the amount of atoms increases, you get more and more anti-bonding and bonding molecular orbitals that are closer and closer together in energy, as you can see here. When you use many atoms, you get a continuous band of energy levels, one called the valence band, which is made from bonding molecular orbitals, and one is called the conduction band, which is made of anti-bonding molecular orbitals. In each band, the molecular orbitals are extremely close in energy, on the order of 10 to the negative 40 joules or 10 to the negative 22 electron volts, which is very small. In between them, you can find the energy gap between them, which is called the band gap. In conductors, the space between the anti-bonding band and the bonding band is zero. This means that the electrons can be very easily promoted from here into here, which is the conduction band, where they can move around, and this is the definition of conducting electricity. For insulators like carbon, the space between the conduction band and valence band is quite large, on the order of 5.4 electron volts. For reference, visible light is on the order of 2 to 3 electron volts, so electrons cannot be easily promoted from the valence band to the conduction band. This explains the poor conduction properties of insulators. For semiconductors, The band gap is in between, so around 1 to 3 electron volts. This means that electrons can be relatively easily promoted from the valence into conduction band. This explains the mediocre properties of semiconductors, the mediocre electrical conductivity. Let's talk about one application of semiconductors. One is the photovoltaic sensor used in solar cells. When light hits a semiconductor, like silicon, with energy, it can promote electrons into the conduction band here. And if we connect the conduction band to a resistor here, that means electrons can move up from the valence into the conduction, and then it can flow into the circuit. This means that we can draw current from the energy provided by light. That right there is a solar cell, an important renewable energy source. This can also be used as a photosensor.
Alright, now let's take a look at a demonstration. So this is the photoresistor connected to an LED, and pay attention to how the brightness of the LED changes when it is receiving light. So its resistance actually decreases when the photoresistor receives light or under luminous conditions. And the principle behind it is actually very, very similar to the solar cell that we just talked about. Anyways, let's look at a specific example here. So let's talk about silicon, right? Silicon has a completely filled valence band and a completely empty conduction band. And when it receives light, the photons promote the electrons from the valence band into the conduction band, as you can see here. And this increases the amount of electron flow in the circuit, thus making the LED brighter. And this actually corresponds to a decrease in resistance because of Ohm's law, which states V equals IR. Since V is constant, when the current increases, the resistance must decrease. Alright, now let's look at how we can make these photoresistors more sensitive. The way we change the conductivity of a semiconductor is by introducing impurities within them. This is also known as doping. So if we introduce something that has more valence electrons than the crystal itself, we will create an N-type semiconductor. So let's look at an example here. So silicon originally has 4 valence electrons, and when we introduce something such as phosphorus or antimony, there will be an extra electron, as you can see here, that is ready to be promoted. On the other hand, if we introduce something that has only 3 valence electrons, then there will be a hole, also known as an electron vacancy. This is known as a P-type semiconductor.
Back to the question, how can we make it more sensitive? In an N-type, the extra electrons are higher in energy than the valence band. They are right here. This is called the dopant level. So they lie up here, close to the conduction band. If we make the photoresistor N-type, you can see how easy it is to promote these free electrons into the conduction band. This will increase the sensitivity and efficiency of photosensors and photoresistors. Another application. Now let's say I hook up a battery to the valence band down here. In that case, it can force electrons here up into the conduction band. And when they fall down, they will release energy equal to the band gap in the form of a photon given by the energy equation, which is hv, or h times the frequency. Using the wave equation, this can be transformed into hc over lambda, where lambda is the wavelength. This right here is what we call a light emitting diode, or LED. And the basic structure of this is a diode, which only allows electron flow in one direction, from the valence to the conduction band work when current is applied. As you can see, we can adjust the wavelength emitted by adjusting the band gap. Let's do some practice problems. Let's walk through some sample problems to help familiarize with the topic. Problem 1. Show that green light with a wavelength of 5 times 10 to the negative 7 meters can excite electrons across the band gap of silicon. How do we solve this problem? First, we need to calculate the critical wavelength of silicon, which is the minimum wavelength or minimum energy of a photon required to cross the band gap. As if you recall, we need to promote an electron from here up until here. So how we do that is we use the equation E equals hc over lambda. We can rearrange for lambda as here equals hc over the energy of the band gap, and then we substitute, and then we find the critical wavelength, which is the minimum wavelength required to promote an electron. We find that it is 1.13 times 10 to the negative 6 meters. But the green light is 5 times 10 to the negative 7 meters, which is smaller. And as if you recall, a smaller wavelength means greater energy. So that means that green light can promote electrons in silicon. Let's do another practice problem. Electromagnetic radiation of frequencies 3.091 times 10 to the 14 Hertz illuminates a crystal of germanium. Calculate the wavelength photoemission generated by this interaction. Germanium is an elemental semiconductor with a band gap of 0.7 electron volts. First, we need to calculate the energy of the incident photon and the energy of the band gap and compare them. The energy of the incident photon is given by h times frequency, and this is to be 2.04 times 10 to the negative 19 joules. Then we convert the 0.7 electron volts into joules, and we find that it is smaller than the energy of the incident photon. This means that electron promotion is followed by the emission of a new photon of energy equal to the band gap, and energy in excess of the incident photon is dissipated as heat. As you can see here in the schematic diagram, the incident photon comes in, the electron is promoted, and then when it falls back down, it re-emits another photon, and we are calculating the wavelength of this. So again, we use the equation E equals hc over lambda. We isolate for lambda, and that equals hc over the band gap. We substitute the numbers, and we calculate the wavelength to be 1.77 times 10 to the negative 6 meters.
Alright, now back to P and N-type semiconductors. So, recall earlier that an N-type semiconductor has one extra electron and P-type has a hole. So, when these two are combined together, the electron from the N-type will naturally want to flow into the P-type, right? And this actually creates a positive charge on the right side and a negative charge on the left side. So this can be explained using the formal charges. So the formal charge is calculated by the number of valence electrons minus the number of bonds plus the number of lone electrons. So here, for phosphorus, it originally has 5 valence electrons, and now after donate the electron to aluminum, it has 4. So we end up with a charge of +1. And on the other hand, since aluminum naturally has 3 valence electrons, you will end up with a formal charge of -1. So this explains the charge buildup. Alright, and recall earlier in the course that we learned about electric fields. So they're created by the movement of electrons and when there is a negative and positive charge on opposite ends. So there will be an electric field force buildup going towards the left side, and as more electrons pass through, this force actually is repelled by the electrons itself, because as you know, like charges repel. And at one point, these two forces will reach a point of equilibrium, and this is known as the constant injection potential. All right, now let's look at some of the practical applications that we have for these transistors. These p-in junctions are what makes up PNP and NPN junctions. And these are what makes up the transistors. And these transistors are what's used in our computer, monitor, our smartphones, and our consoles. So they play pretty much a role in our everyday life. And a large pure silicon wafer has millions of transistors, and it is created using photolithography. And these transistors are actually as small as 5 nanometers. So over the years, they've gotten smaller and smaller because of the advancement of technology. And this has greatly reduced the cost of the electronics. So these are what's used in CPUs, microprocessors, memory chips, and they run on our phones and computers. So as technology gets more advanced, these transistors gets cheaper, and so does our electronic devices. All right, that's the end of our presentation. Thank you for listening.
And we hope you enjoyed.
And conductors, they allow for the move. Yo, what are you doing, bro? I see you in my peripheral vision, bro. You're like moving. Yo, you're like moving, man.
They can form to combine
Restart, bro.
Conditions. And the principle behind it. Yo, what are you doing? What are you doing, bro? Bro. Oh my god, Ryan.
Okay,
Why are you swinging a racket, man?
area of the God.
Here. You have a photo.